no. My sister is sick. I'm not leaving them. My sister is sick. Yeah, I'm just finished the meeting.
Assalamu alaikum. Good morning, everybody. Sorry for bringing you this morning.
In the morning, yes.
Yeah, I know you all want to be at home, me too, but inshallah I won't be too long. My project for this semester was building a supercapacitor that's based on activated biomass carbon that comes from Orange Waste. So to briefly go over what I'm going to talk about, I'm going to talk about the motivation, why I chose this topic.
And why Orange Waste?
Okay. I'll tell you in the motivation. And then I'll give you a general theoretical introduction to supercapacitors, and then how I built my own supercapacitor, and then a brief conclusion, inshallah. So the first reason, and honestly the main reason for me, was that when I looked at the research in the area, it was very open-ended. There were almost no conventions, no norms. Everything is new. Everything is, let's say, being updated almost by the
Every
day.
day.
Yeah, there are so many new papers, so many new ideas, and everything is a possibility. So it's really intriguing. That's why I like quantum computing, actually. The same reason. Also, it deals with energy storage, and why that was fascinating for me was because we're always used to batteries. This is the only real alternative that we have. So, okay, that's interesting. Also, when I heard supercapacitor, I thought, okay, maybe it has double, triple the capacitance. It has much higher. We're talking 10 power 6, 10 power 9 times the usual capacitance, which is really significant. And also it has lots of applications, mainly in electric vehicles. This is the main possible application. So I thought really interesting. In terms of the waste, to answer Dr. Bahrul's question, there's just a modern push to deal with any waste. And to be honest, it could be any other fruit, any other, almost any other food. Most food has carbon. And so the idea is we want carbon. We know we have oranges, especially in the peel and in the seeds. There's a lot of carbon, a high concentration of carbon. So we thought we'd use that to, rather than throwing it away, we'd actually make it useful to some extent.
And why you are looking for carbon?
Yeah,
you
you'll
don't
know.
know anything.
Yeah, I'll tell you why we need the carbon. Okay, so to deal with supercapacitors as a whole, what we know is a supercapacitor. It's a two-plate electrical device with dielectric material in the middle that stores electrical energy. However, there are some very clear limitations. We know the equation, C equals epsilon naught, which is a constant, times A over D. The area of the plates, of the two plates, divided by the distance between the two plates. And so we're limited by these two factors. We can't make a capacitor plate the size of this room if we want to make it really big. And similarly, in terms of the distance, we can only bring them so much close together to where we start having quantum effects. And so if we want to increase the capacitance, and might I add, the typical capacitance is in the picofarad or nanofarad range. With a capacitor, we can reach farads or even hundreds and thousands of farads. So to take that jump, we can't really deal with one or the other in a classical sense. And so what we do is, when we go to nanomaterials, we kind of deal with both at the same time. When we have very small grains, the surface area of the material that we use, it becomes exponentially larger. Rather than having one plate, it's almost like you have 10 power 9 plates, with each grain or each particle being its own plate. And the distance between them are in the levels of nanometers and angstroms between the two, between the metals, between each metal. So it's like you multiply this by 10 power 5, 6, and this you divide it by 10 power 5. So you get a much larger capacitance with a supercapacitor as opposed to a typical capacitor. Now there are types of supercapacitors. The first is the EDLC, or electrical double layer capacitor. I'll talk about them in
So you mean the main layers are the area and the interspacing?
Yeah. And we have a pseudocapacitor and a hybrid, which is a mixture of both. In terms of the EDLC, the EDLC, I mean, we know at the end of the day it's a capacitor, so we want to store energy, electrical energy. It's stored by, let's say, physically, the charge separation. This is where the energy is stored. The way that we do it is, well, we have carbon, activated carbon, and we have usually aluminium as, let's say, as the two electrodes. And so what we do is, when we try to charge the capacitor, we have on one side an aluminium that's plugged to the positive side of the battery or whichever source, and one to the negative. So there's an accumulation of the positive charges here and the negative charges here. And so when we have the electrolyte in the middle, the solution, or it could be a gel or whichever solution we have, there's an accumulation of the negative charges that are being pushed towards the positive side, and the positive ion gets closer to the negative side. And so what you have is two, we say double layers, because you have one layer of charge separation and another one. It's also called the Helmholtz layer. He was the first to describe it. And yeah, the most important thing is the charge is stored electrostatically. And so when we discharge it, the charge difference between them, this is where the energy is. In terms of a pseudocapacitor, the charge is stored electrochemically. And so we rely on the redox reactions to provide us with the energy when we want to discharge. And so typically what we use are metal ions. There are some alternatives, metal oxide, sorry. There are alternatives, but this is the most common use. And so it acts almost like an anode and a cathode. And so with any electrolyte, we have usually acids or bases. So they have a H plus or OH minus. Typically those are the ones used. And yeah, so if you have, we use tin oxide, titanium oxide, I think. With any oxide, we know that when it interacts with an acid or a base, there's going to be a redox reaction. And within a redox reaction, you have H plus ions being transferred. So this transfer, this flow of protons or electrons, relatively however you see it, this is what gives us the current. This is what gives us the energy. A hybrid capacitor, or hybrid supercapacitor, is a mixture of both. So we have one plate, in this case here, as an EDLC, an electrical double layer capacitor, or and here we have a supercapacitor. So it's kind of like you deal with both. Okay, now when we know what a supercapacitor is, we know the different types of supercapacitors. Now we go on to, well, how do we determine the effectiveness of a supercapacitor once we've built it? So there are these three main tests that we use. There are other tests as well. But firstly, we do cyclic voltammetry. With the typical capacitor, we know that it's linear, and so when we can pass linear voltage or linear current through it, and we will be able to very quickly find the capacitance. But that's not the case with a supercapacitor.
You don't pass current through capacitor.
You want to charge
outside
yes,
the capacitor. Something.
Sorry. Yeah, you charge.
Yeah, but break down actually electric field. That if you break the, the direct in between, then it will be destroyed.
Yes.
So
I mean, yeah, when you charge it, absolutely. Yeah, so the equation is linear. Q equals CV. And C equals QV. It's very easy to find it out. But with a supercapacitor, what we have is an electrolyte in the middle, which contains Avogadro number of atoms. And so if you want to pass linear voltage, it would be very, very difficult to get any results, because you kind of want to push, well, literally Avogadro's number of particles. And so what we do is we apply cyclic voltammetry, which is an alternative. Rather than passing linear voltage, what we apply is a sweep rate, or kind of...
you don't pass, you establish a voltage across your whatever element.
Yeah, potential difference between the two electrodes, between the two plates. And so we continuously increase or decrease, so that there's a continuous push of the electrons. And from this, we can see from this derivation. We know C Q equals CV, C equals Q over V. If we take the derivative with time, we know the capacitance is constant. So we have dV over dt. dQ over dt, the difference, the rate of charge time is I, the current. When we multiply it by delta V, we have I delta V times everything. See here the capacitance is I delta V, which is the area of an IV curve, multiplied by delta V times dV over dt. Delta V is the potential window, which is the smallest voltage to the highest, and I'll show you a graph, times the sweep rate, which is dV over dt.
Which your dielectric can sustain. After that breakdown will takes place, what he's telling you.
Yeah.
Yeah, that then current will flow when breakdown takes place.
Yeah.
Otherwise, it's not capacitor, it's a resistor if current
Yeah.
passes through.
Yeah. And that's actually one of the biggest problems with supercapacitors is that they have very high capacitance, but they have low voltage.
Low
rate.
potential window, yeah.
Yeah. So this
Due to this, your electrolyte. If we have solid electrolyte, you can go higher. So.
Yeah. And so, okay, this may be confusing. An ideal capacitor has, let's say, a square shape or a rectangle shape in terms of IV. A resistive capacitor is one that's, let's say, more real in that it has internal resistance in it. We can't really get a completely ideal capacitor. What you have with the supercapacitor is this curve. So when you charge it, you go from usually 0 volts. Where the first there's a spike when there's an initial push of ions or electrostatic push, and then you get to a peak, and then there's almost like crowding in the middle. So there's let's say a decrease in the current that you can attain. And then there's an initial push at the end where after the saturation you come close to the breaking down of your capacitance. And then a similar effect happens when you discharge. So this is the area, I delta V, that's present here. This one. Also have GCD, galvanic charge discharge, which basically measures another strength of the supercapacitor. The supercapacitor has two main strengths. The first is that it can attain, or we can attain through it, very high capacitance. The other thing is that it can give us very, very quick charge-discharge times, which is why it's imagined to be a very a good alternative to batteries.
How quick is quick? You have hundreds of seconds.
Yeah, this is when we want a specific, depends on the current output that you design. But we see here, it's almost close to 0 seconds if you want, for example, the 20 amperes. Also, this is per gram. And so in a realistic case, if you want to build a car to where as soon as you step on the pedal, you get this acceleration, you would build a relatively large supercapacitor.
Gram of what?
Gram of the material that you're going to use.
Material what he deposit.
Yeah.
Make the film.
Which film? Is it the...
Basically, he's making a film because in the beginning, that was the gap what he was talking.
The layers of the capacitor.
Yes,
so
yes.
he is talking about...
TiO2 layer, for example, he makes on
So
aluminum.
the material between the plates.
Yes, the material which he deposits.
The material itself.
Yeah.
Yeah, so we have a plate
Yes.
filled with either Ti2 or metal oxide, for example. This, the
Or
mass of
carbon,
this,
for example. he
or
says.
That's your
Empty.
dielectric. That's your dielectric that you put between the plates of the capacitor.
yeah,
but
we have
that
the
is
electric
electrolyte.
definitely, but we're talking about the material itself, whether it's a metal oxide or carbon, on the plate itself.
Yeah.
So this is almost like the plate, the material that you use to make the plate.
Yeah.
Yeah.
So the specific capacitance, what we call it, that's why he says per gram.
Yeah.
Normally is farad, but we say how many farad per gram.
And what is the dielectric in between?
This the electrolyte.
It's
the
electrolyte,
Yes.
okay.
So this electrolyte actually is polarized. That's why he says in the EDLC, one side if you put electrode positive charge, the other negative side of the electrolyte come closer to it and charge separation to it. Okay, mashallah, good.
Finally, no, this is just a theory. I'll talk about it. Finally, okay, we have here power energy versus energy density.
Yes.
They have a very large power output. But in
Yes.
terms of energy density, it's relatively smaller to, for example, a battery or a fuel cell. Okay, now I'll talk about what I did. This is just the theoretical background. So in terms of preparing the electrode, we start off with any biomass, realistically. I think Dr. Qadad also did it with dates. I'm not
Yes, yes,
mistaken.
yeah, we did. Recently we did dates, yeah.
Yeah, and so it's a long process, but the idea is You start from any sort of waste or any sort of organic product. If you want to use a fresh orange, it's also possible.
To create it.
To obtain carbon, yes.
Yeah.
Because in our case, we decided to build a supercapacitor first with TiO2. I built 3 different supercapacitors and none of them worked. We tried 3 different processes, so I said, okay, we'll do an EDLC, maybe easier. And so I think
I thought when you first look at our environment so dusty with carbon dioxide, why don't you take things from the atmosphere? Why do you have to go to the waste?
It would be ideal, and there's a lot of work in.
And it will serve the environment because you reduce CO2.
Definitely, yeah. And there is a lot of work on carbon capture, which is to convert CO2 waste into C. But it's still a very inefficient process.
Right.
There's a lot of investment from Aramco actually with building 15 on that very research topic. No, they have some very good results. But I think this is more accessible, easier. And so, let's say, okay, we know the supercapacitor, we have 2 plates, okay? If we imagine them to be 3D plates, like this, rather than making a full, rather than having, for example, carbon on the whole thing, it will take, a lot of material to use, and we're still at the research stage. And so we don't make a full carbon electrode. What we have is FTO glass, which is fluorine-doped tin oxide. It's almost like activated glass. It's very popular. You use it to grow thin films, you use it for fabrication processes. What we do is we identify a specific area, usually 1 centimeter by 1 centimeter. Yeah? And this is the area that we put carbon or TiO2 or any other material.
Mm-hmm.
So this acts as our plate to the supercapacitor, rather than having a very large supercapacitor.
Called aerial capacitance cell. The other way, the other units is aerial capacitance cell. Farad per centimeter square or farad per meter square.
And so practically what we do is we write with a pencil to identify the area. We put sellotape here, sellotape here, and sellotape here. And then we apply what's called the doctor blade technique, which is you put lots of carbon here, and then you kind of get almost like a rod, and then press down and kind of smudge it all over, and then do it again and again until it covers the whole thing here.
Unified.
Yeah, and then we do annealing, like Alaa said. Now, sometimes there's a step before, and I think this is where the mistake was. I spent the first 9 or 10 weeks actually synthesizing different types of TiO2, or different, let's say, applying different techniques to get to TiO2.
Why don't you take your pencil and just scratch that surface? Doesn't work.
I think graphite. We want to use
gaps.
we want nanomaterials.
If he has gaps, then there will be not mobility of charge carrier better performance.
So sometimes the synthesis of the material, for example, this whole process, sometimes that takes time as well. But after we do all of this, we do annealing. Usually we reach temperatures of 400, 450 degrees Celsius to make sure that the material that we deposited, carbon in this case, sticks to the FTO glass. So we did some characterization, SEM and TEM. There's a difference between them, but I won't get into it. I don't think I have enough time. And this is the more meaningful results. To be honest, this is probably the most meaningful result in all of supercapacitors, cyclic voltammetry. What we do is we vary the scan rates that we talked about earlier. Should have put the equation. Here we have the sweep rate, which is dV over dt. And this is something that we can control. Here we have the potential window. Okay. Yeah. So we varied the different sweep rates, and what we see is, with increased sweep rate, we get an increased area. And then when we go here, when we find the area divided by dV over dt, we get a decreased specific capacitance per scan rate, which shows an inverse relationship, which is what we had in the equation. We had area over potential window, which we fixed constant to 0.7. We went up to 1.5, but we got some pretty weird results. So we kept it constant at 0.7, which is pretty usual, pretty standard in the literature. So for the same potential window, we have area over the scanning. And so we get a, let's say, negative 1 over relationship, which is what we expect, which is good. And also, as we can see, the capacitance here, specific capacitance is 200 and something, 180 something, as opposed to picofarads or nanofarads. So it's very, very significant.
Farad,
yeah. This is GCD, charge discharge. Again, nothing significant here, but when we go to here, this is when we get some meaningful results. Again, relatively large capacitance. Also, this is I found this very interesting. The power density we got almost 60 to 15, or 120 to 13. When we go back here, we got almost 60 to 15. So we're talking about here. So it's actually pretty efficient. It didn't give us as much power output, but we got pretty good storage, comparable of a typical battery, which I found very interesting, alhamdulillah. This is everything. The most important push was the completion of the cost requirement. Alhamdulillah, we validated our results. We got pretty good results.
What was the validation?
With these tests, just making sure that firstly it works, and secondly that the results are actually impactful. If we got capacitance in the picofarad range, it wouldn't be a supercapacitor, it would be just a typical capacitor. I think the main sort of area are the noises in the environment. We don't have a clean room, I think, here. Also, we found a lot of issues occurring in the when we do the CV and GCD in the wiring issues. It's very easy to have a short circuit. In terms of possible future work, we could change the materials. Also, I think a very good possibility is comparing different types of supercapacitors in some way or other, and maybe finding more applications for them, maybe in phones or in cases where we need a lot of energy. Finally, I want to thank Dr. Gidal especially. He was my advisor, and he really helped in terms of general advising, general life advice, and in terms of giving me papers and continually checking up. And two other people, Mr. Perdana especially. He worked with me for the first almost 10 weeks. He left, I think he's busy. Honestly, if it wasn't for Allah and Dr. Gidal, Mr. Perdana, I don't think I would have done this. He was
No, you did a
incredible
good
help.
job, mashallah.
And Dr. Jafar
Please, so, what experience you gained out of this whole exercise?
Honestly, the main thing is the just opening up to a whole different world of supercapacitors. It was really,
Okay.
really interesting. Yeah.
So, you enjoyed the time, the work?
It was difficult to be in the lab
Yes.
long hours, but yeah, in the end, alhamdulillah, we got.
But research is like that.
Yeah. It's a completely different world.
Yes.
I'm familiar with the theoretical work
Yeah.
with Abdullah, with Rahim. I also have some experience with computation. In terms of pure experimental work,
Yeah.
this is the first time I really have.
Yeah.
meaningful.
It's good to try once in your
Thank you
lifetime.
very much.
Thank you.
Yes.
Why don't you take picture with your students? It's good.
Yeah,
With
let's
the
take.
students.